and I can introduce you our first speaker. So, Muhammad-Waqar Iqbal is a postdoctoral researcher at CentraleSupélec. He earned his PhD in physics from the Université de Lorraine in 2023, supported by the Lorraine Université d'Excellence ICIT program. He previously received DAED, it is a German Academic Exchange Service, funding for his master's thesis at Technical University Dortmund. Over his career, he has received support from multiple national and international funding agencies. His research focuses on photonic hardware for artificial intelligence, with interest in neuromorphic photonics, integrated photonic circuits, optical computing, structured light, and photonic implementation of machine learning algorithms. So please, Waqar, you have the floor. You can start.
Okay, thank you, Mr. Chairman, and also thank you for giving me the opportunity to give an introduction in this webinar on role of optics and neural networks. So without wasting any time, let's start straight away. So I would like to kick off the webinar with this developmental timeline figure from the review paper of Optical Neural Networks, Progress and Challenges, published in Light Science and Applications. This figure provides a compelling overview of the field's evolution, although I would point it out that it's somewhat biased towards integration-focused milestones, reflecting the growing emphasis on compact and scalable hardware. I would just zoom in a little bit in the start. So diving in briefly, the roots trace back to the 1960s through 1980s when Lud laid the groundwork in optical signal processing. And this paved the way for key advances like in 1985, Farhat and his colleagues demonstrated the first optical implementation of a Hopfield model. And soon after, in the community, the formal definition of optical neural networks was proposed. This was by Caulfield and others, not mentioned over here. And just after that, around 1990, Dimitri Psaltis introduced nonlinearity in optical neural networks, and utilizing a photorefractive crystal, and thus enabling more complex computations via optical neural networks. Now, fast forward to the last 10 to 15 years, we have seen an explosive resurgence. Theoretical ideas have crystallized into practical on-chip ONN prototypes, blending photonics with AI for ultra-fast, energy-efficient processing that could redefine edge computing and even beyond. So actually, this snapshot shows ONNs accelerating from analog optics to reconfigurable photonic chips, chasing ultra-fast, efficient AI. Now, to build on this development timeline of optical neural networks, I would like to introduce a pivotal framework that truly bridges computation and photonics. It's the reservoir computing. So emerging in the early 2000s, it was pioneered by Herbert Jaeger with his ecostate networks in 2001, and independently by Wolfgang Maass and his colleagues through liquid state machines in 2002. These two groundbreaking models both fall under the umbrella of reservoir computing, a paradigm where a fixed random reservoir of interconnected nodes projects inputs into a rich high-dimensional space, with only the output layer needed training. I will dive deeper into this framework shortly, but for now, know that it cracked open a world of possibilities for implementing neural networks directly on photonic hardware. Now, just a step back to answer why optics is a good option for implementing neural networks. Now, optics provide a multitude of advantages for implementing neural networks, and the first is the speed and efficiency. Now, by harnessing light for computation, photonics delivers ultra-fast processing at a fraction of the energy cost of electronics. Think of terahertz speeds without the power drain. The next is the massive parallelism. ONN could exploit the light multiple degrees of freedom, such as wavelength, polarization, and phase for parallel operations. And this could significantly boost neural network performance for complex and real-time tasks. Then, thirdly, the optics operations normally have almost minimal heat generation, which means no more thermal bottlenecks. And minimal heat means denser, scalable hardware that stays cool under pressure and perfect for next-gen AI chips. From an application perspective, optical neural networks excel in multimedia signal processing, covering audio, images, videos. And this figure on the right illustrates additional promising domains. Now, before we dive into the optical part, let's again take a quick step back to understand where this idea fits in the broader context of neural networks. So what is a neural network? Imagine teaching a computer to recognize cats and dogs in photos, not by hard coding rules, but by letting it learn through patterns, just like our brains. And that's the magic of a neural network. It's a computational model inspired by biological neurons, but it's a simplified version where interconnected nodes process data through layers to make predictions or decisions. And here is an example of a feed-forward deep neural network. At its heart or at its core, a neural network basically consists of an input layer. You can see this input layer over here, where input data, basically the images, as in this case, the images of cats and dogs. So in general, pre-processing is done on this input images to extract relevant features, which are then fed into the input layer. And then we have multiple hidden layers where nonlinear transformations create feature representations. And finally, an output layer delivering results like cat or dog. Now, during training, the network adjusts its connection strengths or weights over here via backpropagation to minimize errors, enabling it to handle complex tasks like image recognition, language translation, or even self-driving cars. So it's efficient, scalable, and powers AI breakthroughs. Now, here I would like to give a key takeaway from this is that the neural networks are not perfect. They can be black boxes, they can struggle with temporal data, they need large data sets and are computationally expensive. But their ability to generalize from examples revolutionizes machine learning. Now, one very clever alternative to this is reservoir computing. So in the reservoir computing, the recurrent network or the reservoir is kept fixed and only the output layer is trained. This makes it much easier and faster to implement even on physical hardware. And this approach has become a foundation for many hardware implementations, including the photonic reservoir computing systems. Now that we have explored the general structure of a reservoir computing system, let's dive in a bit deeper. So the core idea of reservoir computing is to leverage a nonlinear dynamical system known as the reservoir to map input data into a high dimensional feature space. And this mapping simplifies downstream tasks like classification or prediction by embedding the data in a more expressive, feature-rich representation. So the standout benefit, the reservoir's internal connections stay fixed, no training required, as you see on this figure over here. So this is a normal architecture. You have an input layer, reservoir layer, and output layer, and all the connections from the input to the reservoir layer, they are fixed. The internal connections within the reservoir, they are fixed as well. And we only tweak the output layer weights, which are normally often via straightforward linear regression. So this approach slashes the computational demands compared to recurrent networks, which must fine-tune thousands of recurrent weights. Now, at its heart, it echoes how biological neurons handle dynamic information processing. Now, quick aside from this is that for a curious audience, there is a very related paradigm known as extreme learning machine. It's a feed-forward cousin of, let's say, reservoir computing. Here is, let's say, architecture for this. So you have one single hidden layer. You have, again, the fixed input layers, but no internal connections within. And the data strictly follows along one way. So it's also very good, blazing fast for training static tasks like image classification. Now, if we look at the physical implementations of RC, the magic is the fixed reservoir. If we say why reservoir computing maps easily to hardware, the straightaway answer is the fixed reservoir inside. So the internal connections are random and untrained and kept fixed during the training. So we are skipping the nightmare of backpropagation through time. So it's a pure efficiency for any substrate. We only tweak the readout layer via straightforward linear regression, like ridge or pseudo-inverse. And the training is done in seconds, not in epochs. Now, the best part is any physical system qualifies as a reservoir when it exhibits three essential traits: the nonlinear response for rich feature generations, highest dimensional state dynamics for separation, and fading memory that suppresses noise while retaining context. Now, if we look at the key hardware implementations for photons, includes hybrid like optoelectronic reservoirs, which is a hybrid of light electrons. So the data is injected via lasers. Delay lines in the hardware creates recycled signals for recurrent memory. Photodetectors add nonlinearity. It's super fast, up to sub-nanoseconds for predicting chaotic time series like ML tasks. Then we have photonic reservoirs, which are pure optical setups on chips or in free space using Mach and interferometers, nonlinear media. And then there are some, as for a free space, SLM and DMBs allowed to shape light, and other phenomena like interference are used to generate the transient states. Now, there are also many other hardware implementations for reservoir computing, like analog, electronic reservoirs, spintronic, memoristic systems, and even mechanical and fluidic reservoirs. For us, we would like to focus on the implementation of a photonic reservoir computing system. So let's start with the classical reservoir computing system, which I've just discussed before. So here we have a sprawling network of interconnected nonlinear nodes forming the reservoir. Think of it as a chaotic echo chamber of dynamical system. Now, inputs are injected via spatial light modulators, spreading the signal across the network, while the outputs are captured as pixel intensities from a camera readout. Now, this is an example of a parallel architecture that allows to harvest all the transient states simultaneously, thus enabling the high bandwidth processing for tasks like pattern recognition. It's powerful, but it's demand a full array of hardware nodes. So in some sense, complex and resource heavy. Now let's turn to another clever approach, which was proposed by Apollon in 2011. It's time delay reservoir computing, or TDRC, as shown over here. Now the input is injected either directly or masked to boost non-linearity, and it is fed into a single nonlinear component, such as a semiconductor laser. From there, the signal loops back through a delay line with a total length of tau, creating a virtual reservoir through time multiplexing. And these short time segments spaced by theta basically are the virtual, each serve as a virtual neuron, letting the system's intricate dynamics unfold sequentially. Now, this simplicity or beauty of this is that no sprawling network of nodes is required, just one laser handling the entire computation with elegant efficiency. The fading memory of required for reservoir computing is like emerges naturally from this system, from the natural laser dynamics, projecting inputs into a high dimensional space for linear readout. So in conclusion, for a TDRC slashes hardware complexity while cranking up speed and efficiency, especially in photonics. So if we look at the, let's say, key advantages and trade-offs that you get while adopting this framework, the advantages are clearly the hardware efficiency, high bandwidth, easy scalability, single nonlinear element replaces network of neurons, high bandwidth semiconductor lasers enable gigahertz scale dynamics. While scalability is like number of virtual neurons could be adjustable via adjusting the delay length and sampling rate. And the main drawback comes from sequential processing, which means that a bigger reservoir would be slower. But despite these challenges, Daniel and his colleagues demonstrated a groundbreaking implementation of this scheme, where they smashed through limitations to achieve blazing fast information processing speeds, up to gigabytes per second for tasks like spoken digit recognition. And so here I would show their elegant implementation scheme, experimental implementation. So it's an elegant setup. A lone semiconductor laser serves as the nonlinear powerhouse with inputs injected either optically via Mach Zehnder modulator for intensity modulation, or electronically by modulating the laser diode current. And the signal loops back through a delay line, multiplexing transient states into a virtual high dimensional reservoir. So capturing those rich dynamics of the laser for linear readout. So this setup could also be like all optical, as I mentioned, and you can also have an electronic intense modulation of the current input. I would just quickly show the performance of that setup on the chaotic time series, Santa Fe time series. So here you see basically they have, so the original trace of the chaotic Santa Fe time series is in black. The red shows the predicted. On the top, this is the original time trace for the Santa Fe time series, and on bottom you have the predicted time steps. And you see that the predicted trace of the chaotic time series stays very close to the original time trace. Now, this was the first implementation of almost around the first implementation, such good photonic implementation for a reservoir computing system, and they achieved quite a bit of groundbreaking milestones in that. One of a few of them I've mentioned over here. So they achieved like a blazing fast classification up to 300,000 spoken digits processed per second on the TI-46 audio recognition benchmark. They, in terms of precision, they had a decent, reasonable error rate of around 10%, but they could handle 13 million data points per second. And in terms of energy efficiency, the system, all optical system, just used 10 millijoule per digit in fully optical versus just 2 joule on a traditional computer requirement. Okay, so now a bit on outlook. So looking ahead, the goal is to merge the best of both worlds, like photonics and electronics. So to build the powerful, efficient computing platforms. And we need continued progress in modeling, integration, and novel photonic devices that will drive up on-chip optical reservoir computing forward. And by exploring new photonic materials and ultra-fast modulators, we would move closer to realizing real-time, task-specific optical AI hardware. So I thank you for your attention, and if you have any questions, you can